In the previous lecture, we have been discussing about the properties of systems, and in particular, we discussed three properties in the last lecture. Okay, so those were the system properties. We have a total of 6 properties. Out of the 6, we discussed about 3 properties in the previous lecture. The first was the system having memory or memoryless. Okay. So a system with memory is a system whose output depends on not just the current output but also on the previous outputs. A memoryless system does not depend on the previous inputs. Okay, so a system which has memory, the output of such a system depends on the current input as well as the previous inputs. In contrast, a memoryless system does not depend, the output of a memoryless system does not depend on the previous inputs, rather it depends only on the current input value. And then we talked about the system being invertible or non-invertible. And the third property we discussed was about the causality. Okay, so invertible system is one where for a given system we can produce an inverse system which will do the opposite action of the original system. So if the input of a system is x of t and the output is y of t, then the inverse system will give us back x of t using y of t as the input. So that is what we mean by invertibility. And causality is the system where the output of a system depends only on the current and or past inputs but not on the future inputs. So a system is said to be causal if the output at any point of time does not depend on future inputs. So we call such a system as a causal system. So when we have time as our independent variable, then we cannot have a system whose output at any time depends on future inputs. Okay, so if that system is non-causal, and a non-causal system is not physically realizable. Okay, we cannot implement a system physically in the real world if it is non-causal. So that is what we mean by causality. However, when the independent variable, okay, that is the x-axis variable, is not time variable, if it is some other variable, then it is quite possible that the causal system, the non-causal system, can be implemented. Okay, as in many applications like image processing or data averaging and so on. So when you have a smoothing of functions, right, when you have data which is fluctuating very randomly, we can use some averaging mechanism to get the trend line for the data. Okay, we call this as averaging. And a typical example that I'm going to give you for showing that non-causal system that can be implemented. Okay, I'll make an example for that and we'll discuss that, and then we move on to the next 3 properties of systems that we will discuss. So let me talk about a case of causality where a non-causal system is physically implementable, and that occurs typically when the time axis or the x-axis value is not time variable, rather it is some other parameter. The independent variable is not time in that case. Now, what I'm trying to show here is that in general, a system which is non-causal cannot be implemented in practice because you cannot have an output before an input. But that is when the x-axis value, the x-axis variable is the time variable. But if the x-axis is representing something else, then we can have a physical realization of a non-causal system as well. As we see here, this is let's suppose this is our input signal x of n, and n is some parameter which is not time. Okay, it is some index number. For example, it can be let's say this data is representing the stock market index for week 0, starting from the initial week, and then week 1, after 1 week, after 2 weeks, after 3 weeks, and so on. And it has some fluctuations, right, weekly. Now we can find the average trend to get a smooth curve for this by averaging for each value of n, that is y of n. We will take the average from that current value. We'll take some previous values and some future values, add them together and take the average. Okay, and if you notice here in this case, it depends on the past values as well as the future values. So when this k is minus negative values, it is x of n plus something, right? So that is meaning that it is depending on future values. So let's give some value for m to make a sense of this. So let's say we want to find for n equals let's say 6, and we will take the average. We'll take the value of m to be equal to, let's say, 2. So when we have m equal to 2 and we want to find y of 6, that is for n equal to 6, what is the value of y of 6? Okay, so in that case this equation will become y of 6 as 1 by 2m plus 1, 2 into 2 4 plus 1 is 1 by 5 summation k equal to minus 2 to plus 2 because m is 2 and x of n minus k. So that is basically going to be 1 by 5 times, when k is minus 2, it is x of n minus minus 2, which is x of n plus 2, x of n plus 2. Then it's minus 1, it will be x of n plus 1. When k is 0, it will be x of n. When k is 1, it is x of n minus 1 plus x of n minus 2. When k is 2, right? N minus, let me write that properly, 2. Okay, so basically it is taking for n equal to 6, it is taking the two previous values and the two future values, adding them all together and dividing by the total number of values, which is 5. So you're taking x of n plus 2, n plus 1, n minus 1, n minus 2, right? So this n plus 2, n plus 1, these are the future values, right? When we are trying to find x of 6, n is 6 here, so x of 6 plus 2 is going to be x of 8. So this is our point of interest. We want to find what will be the value of y when n is equal to 6. So that is basically x of 6 plus 2 is x of 8, which is this. X of 6 plus 1 is x of 7. X of n is x of 6. X of n minus 1 is 6 minus 1 is 5. And x of n minus 2, 6, which is 6 minus 2 is 4. So it's going to take these 5 values, which I'm going to put in a box here. So it's going to take on, so to find y of n when n is equal to 6, it is going to take the values for 7 and 8 as well as 5 and 4. So to compute y of n at n equal to 6, it is depending on not just the previous two values and the current value, but also on the next two values. Okay, now this is possible when this n is not our time value, but rather we have some data which has been collected over a period of time and we want to just take the averaging of these. So that gives us an average, right? So that's like a moving average. So when we have n equal to 7, when we move to 7, it will take the two future values, which is 8 and 9, and the two past values, which is 6 and 5, add them all together and divide by the total number of values, which is 5. So that gives us an average, right? So basically this equation is giving us what is called as a moving average. But what we notice here is that for any index value n, the output y of n depends on the future inputs, the input values at the higher index, right, which are to the right of it, as well as the past indexes. So this is a non-causal implementation, but it is physically realizable because the x-axis here is not representing time. So we call it as moving average. So this is what I wanted to highlight here. In general, causal systems where the time is our independent variable, if it is non-causal, we can't implement it in physical reality. But if it is causal, it can be physically realizable. However, it does not mean that non-causal systems are of no use to us. Okay, there are many instances where our input-output relationship exhibits a non-causal relationship, and it is still physically realizable. And that is particularly true when we have the x-axis as some other independent variable other than time. So if I just elaborate this a bit further, so we can write this y of 6 as equal to 1 by 5 times x of 6 plus 2 is x of 8 plus x plus 6 plus 1 is x of 7 plus x of 6 plus x of 5, that is 6 minus 1 is 5, plus x of 4. Okay, so that's our output when n equal to 6. So it's depending on the input at n equal to 6, the past inputs which is 5 and 4, and also on the future inputs x of 7 and 8. Okay, so it appears that it is non-causal and therefore it cannot be physically realized, but this is implementable when we have this data already available with us. Okay, so this information is available with us already, so at any of these times we can take the current and future values, add them together and take the average, as in this example. But if it's a system where the future input values are not available to us, then we can't do it. Okay, so now that's when we have time. Okay, when we can't get an output before an input. Okay, so that's to explain a case where a non-causal system is physically realizable. But in general, a system which is non-causal, it cannot be implemented in reality. Let us now move on to our next property, which is property number 4, and it's called as the stability property. Okay, so in today's lecture we are going to talk about 3 more properties of systems, and the first of those 3 is the stability property. And what we mean by stability is that if the input to a system is bounded, then the output is also going to be bounded. Only then the system is stable. Or in other words, we can say that the system is stable if, after giving an input, the system produces an output, and after producing that output, after a certain time, the system will come back to its initial position. Okay, that is the position when it was that it was in before it got the input. So if the system returns back to its original state, we call this as a stable system. Or in signals and system terms, we say that if the input is bounded or limited, if we give an input that is having a limited magnitude, the output will also be having a limited magnitude. It will not grow indefinitely. Okay, that is what we mean by a stable system. So let's write the definition formally. So what this means is that when a system is having an input which is bounded in its magnitude, then the output will also be bounded by a certain magnitude, not necessarily the same magnitude as the input, but by some other limit. There will be an upper limit to the maximum value or the magnitude of the output signal as well. So if we say that the input is some arbitrary signal, okay, it can be any signal, let's say, but it does not exceed this upper bound, okay, in magnitude on the positive side as well as on the negative side. So the signal lies between these bounds. Then the output that the system produces will also be bounded by some values, okay, and it will not produce an output which is unbounded for an input that is bounded. That is what we mean by a stable system. So in this case, let's say we have some other limits of the bound for the output signal. So we may have the output something like this. So it is bounded between these limits here. So let me redraw that a bit properly. One more time. So it's some arbitrary output coming from the system given this particular input signal. So if the input is bounded by some limits, then the output is also bounded by some limit, and that is what we call by a stable system. In contrast, an unstable system will produce an output which is unbounded at some point of time. Okay. Now, for example, if the system is unstable, then an input which is bounded like this may produce an output. Let me change the font here. May produce an output which is something like this. It's growing. Okay, the red one, at some point it has crossed the bound and it is continuing to grow. As we keep giving the input. So that means the system is unbounded. So this is what we mean by the stability of the system. A stable system produces a bounded output for a bounded input, and in contrast, an unstable system produces an unbounded output even when the input is bounded. So such a system which produces a bounded output for a bounded input, we call it as a BIBO system or BIBO stable. Okay. So it's called as bounded input, which is BI, and bounded output, which is BIBO. Okay, bounded input, bounded output, stable system. Okay, if the output is unbounded, even when the input is bounded, then it becomes an unstable system. So an example for a stable system, which we have already seen in the previous slide, is this averaging thing. This is a stable system because at any value of n, we are taking the average of the previous and past values. And if these input values are bounded, for example, if these input values, if we say they have a bound, then the average value will always be bounded with that same upper limit, right? So let's say if the maximum value for these input signal impulses is 5, and if you're taking the average of the future two and the past two and the current one together, if you take the average of those finite number of samples, then the average is going to be less than or equal to the highest value that is available there, right? So if the input is bounded, the output is bounded. So this equation, the system which is a moving average system, is a stable system because when the input heights, okay, when the magnitude of the input signal is bounded, the output signal will also be bounded by that same bound, because we are taking the average of a finite number of samples. Okay, so that's a stable system. Now we'll look at an example of a system which is unstable. Now, to check whether the system is a stable system or an unstable system, we can use a very simple input signal x of t and check whether, if that input is bounded, whether we get a bounded output y of t or not. So let's say the input to the system x of t is a constant. So if we choose x of t equal to some constant, let's say 1. So if the input is a constant, that means for all values of time, the input signal x of t is a constant value, which is 1. So that's x of t and t on the x-axis. So the input is bounded. The input is not growing out of bounds. It is limited to having a value of 1 at all times. And of course, we can go on the negative side as well. So the input is bounded. And when the input is bounded, what is the output in this case? So for all values of time t, x of t is equal to 1 for all t. So in that case, the corresponding y of t is equal to t times 1, which is equal to t. So that means the output is going to be growing out of bounds, because if we plot the input-output relationship, so that's our t on the x-axis and y of t on the y-axis, then for each value of time t, the output is equal to t. So when t equal to 1, y of t is equal to 1. When t is equal to 2, y of t is equal to 2. So it's going to be a line like this, right? So that means it is growing out of bounds, even though the input is fixed at 1. The magnitude of the input is fixed at 1. The magnitude of the output is going on increasing and increasing and increasing as time increases. As when t is a million, the output is a million. When t is 10 million, the output is 10 million, right? Because y of t is equal to t. So this is an example of an unstable system, because even though the input is bounded, the input is not exceeding 1, the output is unbounded. It is going on increasing with time. So this is an unstable system. Now we'll also look at another example of a stable system, where the input-output relationship is defined as y of t is equal to e power the input, e power x of t. So we will see now this is a stable system because when the input x of t is having a bound, okay, if it does not exceed a certain value, then the output will also be bounded by a certain value. So let's say in this case x of t is bounded. Okay, let's say if x of t is bounded between minus b and plus b, some value. Okay, so that means x of t is having some arbitrary signal whose amplitude lies between minus b and plus b. For example, this upper limit is plus b and lower limit is minus b. So the value of x of t is going to be somewhere between minus b and plus b, and it is never going to exceed that b. Okay, so in other words, we write that the magnitude of x of t, so magnitude of x of t is bounded by b, or x of t is lying between minus b and plus b. In that case, what happens to y of t? Y of t is going to be bounded between e power minus b and e power plus b. The maximum value for x of t is plus b and the minimum value is minus b. So when x of t is having the highest value, which is plus b, y of t will be e power plus b. And when x of t is having a value of minus b, y of t will have a value of e power minus b, right? So in this case, what we see is that y of t, then y of t is also bounded, but the interval or the limits of the bound are between e power minus b and e power plus b. So when x of t is having the maximum value of plus b, the output y of t will have the maximum value e power plus b. And when x of t is having the minimum value minus b, then the output will have e power minus b. It will not be anything outside this range, right? Because the input is bounded, the output is also bounded. So this is a stable system. So we have this as an example of a stable system. So we need to check based on some input signals and see whether a bounded input produces an unbounded output or not. If we notice that a bounded input produces an unbounded output, then the system is unstable. If any bounded input produces only a bounded output, then the system is stable. So now we have seen the fourth property, which is the stability of a system. We now move on to the fifth property, which is called as the time invariance property of the system. So that's property number 5, which is called as time invariance. Now, time invariance means that the behavior of the system is not changing with time. So if we have a particular system, and to that system, if I give some input and I get some output today, and if I repeat the same experiment tomorrow, right? If I give the same input to that same system tomorrow, I expect to get the same output tomorrow as well. So the behavior of the system is not changing with time. So in that case, we say that the system is a time invariant system. Now, in terms of the notation that we have used so far, like time scaling, time shift, and so on, that is the notation of signals and systems. In that notation, we can describe time invariance if, for example, a system whose input x of n produces an output y of n. Okay. Now, if the input gets shifted by a certain amount, then the system's output should also be shifted by the same amount. Or in other words, a system whose input-output relationship is given such that a given input produces a certain output y of n, then if the input is shifted by a certain amount, let's say x of n minus n naught, it is shifted by a certain amount, then the output should also be shifted by the same amount, y of n minus n naught. So when the input is x of n, we get the output as y of n. And if the system is time invariant, if the input is x of n minus n naught, then the output will also be a shifted version of the original output that we had when the system was input was x of n. So an input x of n produces an output y of n. If the input is shifted by n naught, then the output of the system should be a shifted version of the corresponding output y of n. In that case, we say that the system is time invariant. And similarly, if we had to say this for the continuous time, so if we have to write this relationship for continuous time, okay, this is what I have written for discrete time. Okay, for continuous time, the input-output relationship would be, for example, if we give an input x of t, it produces an output y of t. If the input to this system is a shifted version of x of t, which is x of t minus t naught, then the output to the system would be a shifted version of the output y of t, which is y of t minus t naught. If this condition is satisfied, then the system is time invariant. So these are the conditions for time invariance. And any system that satisfies this property is called as a time invariant system. So now let us look at a few examples and to demonstrate how to find whether a system is time invariant or not. So we'll start off with an example where we have the input-output relationship given as the output y of t is equal to the sine of the input x of t. Okay. If we have this input-output relationship, we want to check whether this system is time invariant or not. So for that, what we will do is we'll first consider a signal, input signal x1 of t, and denote the corresponding output signal as y1 of t. So we will say that if input is x1 of t, then output is y1 of t equals sine of x1 of t. Okay, so that's the input. When the input is x1 of t, we get an output y1 of t, which is equal to sine of x1 of t. Now, if we choose a second input, which we will define as x2 of t, so consider second input x2 of t, which is a shifted version of x1 of t. So x2 of t is nothing but x1 of t minus t naught. So we have x2 of t, which is a shifted version of the original the initial input x1 of t. Now the corresponding output will be called as y2 of t, corresponding output y2 of t is equal to sine of x2 of t, but x2 of t is equal to x which is equal to x1 of t minus t naught. So sine of x2 of t is x1 of t minus t naught, right? But we see now sine of x1 of t is y1 of t. So here sine of x1 of t is y1 of t. So sine of x1 of t minus t naught. So if we change this to t minus t naught, this y1 of t minus t naught. Okay, this y1 of t will also become y1 of t minus t naught. So now if you look at this equation and compare it with this particular equation, so y2 of t is sine of x1 of t minus t naught. So sine of x1 of t minus t naught is going to be y1 of t minus t naught. So we will have it as y1 of t minus t naught. So what we notice is that when the input is shifted by a certain amount t naught, then we get an output which is also shifted by the same amount. So it's when x1 of t has been shifted by t naught, y1 of t is also shifted by the same t naught, okay, and in the same direction as well. So y2 of t is y1 of t minus t naught. So basically what we say is that y1 of t minus t naught is equal to sine of x1 of t minus t naught, which is what we have here, right? So a shift in the input produces a corresponding shift in the output as well. So this system is a time-invariant system. So in other words, when the input is x1 of t, we got the output y1 of t. Now when the input is x1 of t minus t naught, then the output is y1 of t minus t naught. So the input, any shift in the input produces a corresponding shift in the original output as well. So therefore this system is time invariant. That means its characteristics or properties do not change with time. Okay, so it's a time invariant system. This is how we check whether the system is time variant or time invariant. Now let us look at another example, and we'll see, and we'll in this case look at an example of the discrete case. Okay, so let's say I'll call this as example 2. So if we have y of n equals n times x of n. So now the input-output relationship is given as the output is equal to n times x of n, and we need to check whether this signal, this system is a time invariant system or not. Now in all these investigations, when you want to check whether a system is a time invariant system or not, whether it's a stable system or not, our basic signals come very handy. So we have seen our basic signals previously, like the unit impulse function and the unit step function, right? So we can use these very simple and important functions as our input signals, and then verify all these properties of the system. So we can utilize these signals, the basic signals, to verify our properties. So in this case, to check whether the system is time variant or not, or whether it is time variant or time invariant, we'll choose x of n to be a delta function, a very simple function which is unit impulse function. So consider x of n, okay, x of n equal to delta of n, okay, delta of n. Now you know that delta of n is an impulse at n equal to 0. So it is an impulse at n equal to 0. So that's delta of n. It's discrete, so we put it in square brackets. So only when n equal to 0, its value is equal to 1. For all other values of n, the value of delta of n is 0. So when we give such a signal as an input to the system, we will get y of n. In this case, y of n will be n times x of n. So this delta of n is 1 for n equal to 0. So 0 into 1 will be 0. So y of n is equal to 0 in this case. Okay. Now if we give a shifted version of this input, of this delta function as input to the system, we want to check whether this y of n is also a shifted version of this y of n that we have here. So let's see, if x of n is shifted, that is to the right, for example, x of n minus n naught, okay, then we'll have it as delta of n minus n naught, right? So let's fix some value for this n naught, okay? So let's say it is shifted by choose n naught equal to 1, for example. That means x of n minus 1, which is delta of n minus 1. In this case, the input signal x of n is an impulse at n equal to 1. So that's n and that's x of n, all right? It's an impulse when n equal to 1. So in this case, if that becomes our input signal, then the output y of n, which is equal to n times x of n, which is equal to n times delta of n minus 1. Now, delta of n minus 1, because we have chosen x of n as x of n minus 1. It is a shifted version of the original delta of n, which is delta of n minus 1. So it is n times delta of n minus 1. So that's equal to 1 when n equal to 1. So the height here is 1. So that's equal to 1 when n equal to 1. For all other values, it's 0. So it will become equal to 1 into 1, because when n equal to 1, we will get delta of 1, right? So we will get this as equal to 1. And that is true for n equal to 1, right? So for n equal to 1. But in general, y of n is going to be, so n times delta of n minus 1. Okay, let me write that properly. Now we notice that when the input signal is an impulse delta of n, the output is 0. Okay, we'll call this first output when it's an impulse as y1 of n. Now a shifted version of the impulse, okay, if this impulse is shifted by 1, we get delta of n minus 1. The output that we get here, we'll denote that as y2 of n, okay. The y2 of n that we have here is not a shifted version of the input, clearly, because the original input is output is 0 when input is delta of n. But when input is delta of n minus 1, the output is n times delta of n minus 1. So what we see here is that this y2 of n is not a shifted version of y1 of n. Okay, the system is time invariant only if a shifted version of the input produces a corresponding shifted version of the same output, right? So when the input is shifted by 1, the output y1 of n should also be shifted version of this, right? So y2 of n, if it turns out to be y1 of n minus 1, then it is time invariant. But in this case, it is not the case. Okay, y2 of n is not equal to y1 of n minus 1. So we see here that y2 of n is not equal to y1 of n minus 1, because the input here is shifted by 1 to the right. The output is not correspondingly shifted, because if it was 0, a shifted version of 0 should also be 0, right? But that is not the case. In here, y2 of n is n times delta of n minus 1. So y2 of n is not a shifted version of y1 of n. So we say, i.e., y2 of n is not a shifted version of y1 of n. Okay, so the system here in this case is a time variant system. That means it's changing with time. So the input-output relationship is changing with time. So we say that this is a time variant system. Okay, so the previous example that we saw is a time invariant system. That means its characteristics are not changing with time. Here the system's characteristics are changing with time, so we say it's a time variant system. And to understand this further, I want you to look at the example in the textbook. So look at the example which is example 1.16 in the textbook. Okay, so I want you to look at the example and have a clear understanding of it, and that it has a graphical representation to show a particular system which is not time invariant. Okay, it's a time varying system. So I want you to look at this particular example in the textbook, and that will make things clear for you. I've given you two examples here, and I want you to look at this one more example in the textbook to make things clear for you. So I recommend that you look at this example, read the entire passage given in that example, the entire explanation, and also look at the figures given there to get a clear understanding of what is happening, or how we determine whether a system is time variant or time invariant. Okay, now time variance or time invariance is an important property, because in much of the next chapter we'll be dealing with a specific type of systems which are time invariant systems. Okay, if the system's characteristics are not changing with time, then there are a special class of systems called time invariant systems, and much of our next chapter is dedicated to time invariant systems. So I recommend that you look at this example 1.16 in the textbook, which is on page number 52, very carefully and get a clear understanding. Okay, I've already given you two examples of time invariant systems. I've given an example here for a time invariant system and another example for time variant system. So you will look at this example 1.16 in the textbook as well, and develop a clear understanding of what we mean by time invariance. The next property that we are going to talk about is called as the linearity property. So that's the property number 6 that we are going to come across. It's called the linearity property. And what do we mean by linearity property? So suppose a system takes in some input x of n. Okay, I'm writing the case for the discrete case, the example for discrete case, and similar things apply for the continuous time case as well. So an input x of n to a system, let's say, produces an output y of n. Okay, now if we give some other input, okay, which we'll call as x2 of n, let's call this x1 and y1. Okay, if the input is x2 of n, and the corresponding output, let's call it as y2 of n. Okay, so an input x1 of n produces an output y1 of n. An input x2 of n produces another output which we denote as y2 of n. Now, if we add these two inputs together and give it as a single input to the system, what will be the output of the system, and under what conditions we will say that the system is linear or not. So if the input to the system is a linear combination of x1 and x2, okay, of the original inputs x1 and x2 is a linear combination of x1 of n and x2 of n, that is some constant times x1 of n plus another constant times x2 of n. Okay, so if we define another input x of n, which is a linear combination of these two inputs x1 and x2 of n, so it is some constant a times x1 of n plus b times x2 of n, then the output to the system, which has this linear combination of x1 and x2 as its input, okay, if the output of the system with x of n as input is y of n, which is a linear combination of the individual inputs when we had the x1 and x2 as separate inputs. Okay, so that means y of n is a linear combination of y1 of n and y2 of n. So x1 of n separately gave the output y1 of n, x2 of n separately gave the output y2 of n. Now we are giving an input which is a combination of x1 of n and y2 of n. That should produce an output which is a linear combination of the separate outputs y1 of n and y2 of n. So this combined output is y of n is a times y1 of n plus b times y2 of n. Okay, the same thing applies for continuous time as well. Instead of the parameter here being n in square brackets, we'll have it as t in round brackets or parentheses, right? So if this condition is satisfied, then we call such a system as a linear system. Okay, so then we call this as a linear system, or in other words, we say that the system satisfies the linearity property. Now here we can choose our values a and b as 1. So if it is 1, a equal to 1 and b equal to 1, it is the combined input is x1 of n plus x2 of n. The corresponding output will be y1 of n plus y2 of n. Or if it's continuous time, it is x1 of t plus x2 of t produces an output y1 of t plus y2 of t. So we call this system which satisfies this property as a linear system. So we can write this in, we can break this down into many ways. For example, now I'll write it in the continuous time as well. So if we have x1 of t as input, and if it produces an output y1 of t, then if we multiply the input with some constant a times x1 of t, then the output should be a times y1 of t. Or if we have x1 of t, suppose x2 of t produces an output y2 of t, okay, then x1 of t plus x2 of t should give us an output y1 of t plus y2 of t. So x1 of t gives an output y1 of t, x2 of t gives an output y2 of t. So if we combine the two inputs, the output that we get should be the sum of the individual outputs, which is y1 of t plus y2 of t. Okay, so basically I made the a and b as 1 here. So a equal to 1, b equal to 1, and I've used the continuous time notation here. So a system which satisfies these properties is called as a linear system. Like this, we can add many symbols. For example, if the input is x1 plus x2 plus x3 plus x4, then the corresponding output would be y1 of t plus y2 of t plus y3 of t plus y2 of t. Okay, so this property here is called as the additive property, and this property here is called as the scaling property. So if the input is scaled by a certain factor a, then the output is also scaled by the same factor a. So x1 of t gave y1 of t, a times x1 of t gives us a times y1 of t as the output. So if the inputs are added, then the corresponding outputs are also added. Okay, that is called a system which satisfies these properties. Okay, this property as well as this property is called as a linear system, and both these properties have a specific name, and this is called as the scaling property, or it's also called as the homogeneity property. That means the system is homogeneous system. Okay, if this property is satisfied, we call it as homogeneous system. Let me write that clearly. Okay, and this second property that we have here, this is called as the additive property. Okay, this is the so if we add certain inputs, then the outputs will be the corresponding sum of the corresponding individual outputs. So a linear system satisfies the scaling property or homogeneity property as well as the additive property. So if we now combine both these properties and say, let's say we have an input x of t, which is a linear combination of the individual inputs, okay, which is x1, x2, x3 and so on. Okay, so we can call it as summation xk of t for k equals 1 to whatever. Okay, for k equal to 1 to some n. We can have n such inputs, and each of these can be scaled. Okay, so we'll multiply each of these with a scaling factor xk. So this is a1 x1 of t plus a2 x2 of t plus a3 x3 of t up to an xn of t. So if we have such a linear combination of inputs to give us a new input x of t, so we can write this as a1 x1 of t plus a2 x2 of t plus so on and so forth up to an xn of t. So okay, if we have, or this can be many more as well. Okay, I've just fixed it at the upper limit of xn. We have n such input signals combined together to give us a new input x of t. For a linear system with x of t as input, suppose x1 of t produces an output y1 of t, x2 of t produces an output y2 of t, and xn of t produces an output yn of t. Then for a linear system, the corresponding y of t will be the summation of the corresponding outputs yk of t. So it will be ak yk of t for k equal to 1 to n, which will basically be a1 y1 of t plus a2 y2 of t plus so on and so forth up to an yn of t. So this property that we see here is called as the superposition property. So we write this as superposition. So basically it's a combination of the scaling property and the additive property. So if the inputs are the scaled and added versions of the original inputs, okay, a1 x1 of t plus a2 x2 of t plus a3 x3 of t, then the corresponding outputs are also the scaled and added versions of the corresponding output signals. So we call this property as the superposition property. So that superposition property holds or is valid for a linear system. Okay, I will stop here for today and I will continue my discussion on linear systems further in the next lecture, and we will then give some examples also, and finally we'll be using all these concepts. Okay, this is the last topic of the first chapter, and we'll be using all these concepts in our next chapter, which deals with what we call as linear time-invariant systems. So the last property, which is linearity, and the property before that, which we saw, is the time-invariance. So we'll be looking at specific systems which satisfy the time-invariance property and the linearity property, and we call such systems as linear time-invariant systems, and we'll dive into that topic in the next lecture. Okay, so I'll be giving an example of some more discussions on linearity, and then move into what we call as the linear time invariant systems and the analysis of linear time invariant systems in the next lecture. So far I have been going quite slowly because these are very important fundamental concepts which will be used in the next chapter. Now you are expected to read these concepts and come prepared for the subsequent future lectures, because all these properties and the signals that you have seen previously will be used in our chapter 2 when we discuss the analysis of linear time invariant systems. So I'll be going quite fast there, so you need to revise these previous lectures before coming to the lectures from next week. So it is important that you keep revising these topics and practice the tutorial exercises given to you by Engineer Zishan as well. So make sure that you are revising the previous lectures and coming for your next lectures.